Welcome back to ECE 320A. We're still in Unit 10, which is our Bode plot unit. Appendix E is the textbook material for that, and homework 10 is what you need to complete at the end of this unit. In these last couple of videos, we're talking now about putting all of the pieces together. And in this particular video, we want to sketch the Bode plot for h sub 2 of s, which is 100s over s plus 0.1 times s plus 10. We have two poles, we have 1, 0. The 0 is at the origin, so that's going to give us this continually sloping line, and the poles will kick in at their appropriate break frequencies. Now I'm talking the magnitude behavior. We have not only the magnitude behavior, but the phase behavior. All of those poles, as you can see, we had positive coefficients. So those were all minimum phase transfer functions. Poles and zeros are all in the left half of the complex S-plane. We'll sketch the individual terms, and then we'll add all of those pieces together. And we'll maybe do this one a little bit more quickly than what we've done in the previous video. Here's our pole zero form for the transfer function. We can factor out the constants that are not equal to 1 yet, and so now we have our two pole factors in time constant form, and so the entire transfer function is now in time constant form. And in this particular case, the 0.1 and the 10 nicely combine when multiplied to equal 1, so we still have a gain of 100 in the numerator, and we have our 0 at the origin. Let's now make some observations before we start sketching as a way of maybe grounding our expectation as to what we should expect. For low frequencies, what's the slope of that transfer function? In this particular case, what do we have happening at low frequencies? And when we start talking low frequencies, what are we meaning? Well, typically that means a decade or more before any of the breaks would occur. In this case, our first break is occurring at 0.1, and we have something that's always on in terms of sloping behavior because of that 0 at the origin. So if we go to 0.01 in frequency, we could consider that a low frequency. And what's the slope of the magnitude at that frequency? Well, because we have that 0 at the origin, it's upstairs. We have one of those. And so, in fact, this slope of h sub 2 at low frequencies, I would say, is then plus 20 dB per decade. And that's because of the 0 at the origin. If we had a 0 somewhere else, then we could have a slope of our magnitude being 0 at low frequencies. That's possible. What's the phase of this transfer function, this particular transfer function at low frequencies? Well, the two poles are breaking, so they don't contribute any phase for low frequencies. At frequencies 0.01 or less, those two poles are contributing 0 degrees. The gain is positive. It's not contributing any phase, but we still have that something happening at the origin. It's a 0 at the origin, and that's always going to be giving us a constant angle, and that angle, because of it being a 0, is a positive 90 degrees. Like we identified low frequency behavior, we can also identify high frequency behavior. In this case, what's considered high frequency? Well, we go out to the right beyond what might be already have broken or have changed or stopped changing. If we go a decade beyond the highest break, in this case our highest break is happening at omega equal to 10. So if we go out to 100 in frequency, that could be considered high for this particular transfer function. And what were we asking? What's the slope of our magnitude at high frequencies? Well, we have plus 20 dB per decade due to the zero at the origin. Then we have minus 20 dB due to that pole at point 1. So now we have a plus 20 and a minus 20. We're now flat in terms of slope of our magnitude, and we haven't yet gotten out to our high frequency. At 10, we kick in another slope down due to that pole, and so now we're a net slope of minus 20 dB per decade, and that doesn't change after that last pole becomes active or kicks in or breaks. So in fact, we have a slope for high frequencies, let's say for omega equal to 100 or more, that's now at minus 20 dB per decade. And we could actually sort of reason that without going through the walking from small frequencies to high frequencies that I just did. We could say, oh, we have two poles and we have one zero. And what's happening at high frequencies? Well, it's really the net effect of those singularities, or what is the pole zero excess, or how many more poles do we have than zeros? Well, we just take 2 minus 1. I think I can even do that math. So we have 2 minus 1. That gives us 1. Our pole zero excess is 1. So that effectively says at high frequencies, we have one pole that's acting. Let me just try to write that down. Effectively, a pole, or one pole, at high omega. That's due to the pole zero excess. If we had a pole zero excess of 2, we would then have 2 times minus 20 dB per decade, or we would be sloping at high frequencies at a rate of minus 40 dB per decade. And what we're doing is we now are establishing some ways of checking our work or our sketch. We should expect a plus 20 dB per decade in our magnitude slope for low frequencies, and we should be falling off at minus 20 dB per decade for high frequencies. And what's the phase of our transfer function at high frequencies? Well, now that we've done this pole zero excess thinking, we now know we have one pole in effect at high frequencies, and one pole contributes minus 90 degrees. And that's now another way that we can check our phase plot. We know we should be ending up at high frequencies having a phase of minus 90 degrees. At low frequencies, we're starting at plus 90 degrees. So that gives us a way to check our work as we're drawing these Bode plots. Let's now do the magnitude. Our constant was 100 in this case. So we now take the log of 100, that's really 2, and 2 times 20 is 40. So our constant is now 40 dB, and that's going to be contributed for all frequencies omega. And I've now sketched that in blue. Here's our 40 dB sketch. We had a 0 at the origin. That's this line that's going up to the right. That's due to our 0 at the origin. And now we had two poles. We had one pole at point 1. That starts breaking at point 1. And that's going to be here, and it's going to be going down. So that's now contributing that piece. And we had another pole at 10, and that will kick in at 10. So that's now here. It'll be minus 20 dB at 100, minus 40 dB at 1,000. It's now going down here. And those are all of those sloping lines are at either minus 20 dB per decade for the poles or plus 20 dB, because they all were just single poles or zeros. Now let's put all of these pieces together. And by that, we need to move to the left. I'm pushing my hands over to the left. I'm focusing now on the left side for low frequencies. We now need to go over to the low side and say, okay, what's happening at low frequencies? Well, at low frequencies, let's just see. We have our gain. That's always 40 dB. Let's go back far enough. Let's go to 10 to the minus 3. And the 0 at the origin is contributing minus 60 dB. So we have minus 60 plus 40. That's going to be giving us minus 40 dB at 10 to the minus 3. Then at 10 to the minus 2, we have 40 dB of our 0 at the origin, and we have plus 40 dB due to our... Now what am I doing? Wake me up. We had minus 60 plus 40. That's going to give us minus 20 dB. Thank you. Had a bug in my ear telling me something wasn't quite right. So now we are at minus 20 dB at 0.001 or 10 to the minus 3. At 10 to the minus 2, we have minus 40 dB plus 40 dB or 0 dB. And we're coming up from the bottom, so that's going to always be happening in our magnitude plot. Nothing changes until we reach this point, and at this point, or at point 1, we have a pole kicking in. That pole is sloping down the same amount as the 0 at the origin was sloping up, and so now we have a net slope of 0 until we hit another pole or 0 break. And that's not going to occur until 100. So now I can connect those dots. And if you're drawing this, I would get a ruler and just quickly draw that out. And now, after this point, we have the second pole kicking in, and it contributes 20 dB down for frequencies beyond 10. And so now we can simply say, oh, our net slope is minus 20 dB. And that's now our magnitude plot for this particular transfer function. In the phase plot, what I've actually indicated are some up and down arrows to sort of guide us through this process. We start actually with the angle due to the 0 at the origin, and that's a plus 90 degrees. So let's go ahead and just say, oh, this is the 0 at origin. That always contributes 90. Then we have a pole that kicks in at, or it is centered at 0.1. So now we're going to have a transition over a 2-decade interval. It's going to go down. The slope is going to change in a negative direction, and then it's going to flatten out. That's what my up arrow means. So this is now the phase due to the pole at 0.1. It starts at 0.01 and ends at 1. And then we have a pole at 10. And that pole actually then has phase transitions over a 2-decade interval. So it's going to be 0 degrees to minus 90 degrees from 1 to 100. And now we want to combine all of those pieces. So if we go far enough back in frequency to the left, we start at plus 90 degrees. Everything else is contributing 0. We'll be flat until we reach something that starts sloping, and that doesn't happen until we reach 0.01. But at that point, we actually start coming down at 45 degrees per decade. Again, 45 degrees per decade. That particular pole, its phase contribution stops, but then a new pole's phase contribution kicks in, and we now just follow that particular phase all the way down and then it stops, and we just go flat from there on after. And we should be ending at minus 90 degrees, starting at plus 90 degrees, and we simply connect those extremes with a straight line. So this is now the total phase plot. We had our total magnitude plot, and that's now what is involved in sketching. And this actually should have been h sub 2, I believe. This is now h sub 2 for our plot. And we can check that against MATLAB. I've done this prior to making this video, and here are the commands. We enter in the numerator and the denominator. I actually illustrate how you can multiply two polynomials together. In MATLAB, that involves the convolution operation. So we convolve one factor in the denominator with the second factor, and that now gives us the denominator. We can check the roots. We had a 0 at the origin. We had poles at minus 0.1 and minus 10. We can build up the transfer function object using the TF function and simply now issue the Bode command. And if we wanted to, we could do the 0 and pole on that transfer function. But the Bode plot now should look similar to what we have sketched in our particular hand-drawn sketch. We're coming up from the bottom in the magnitude at a plus 20 dB per decade, and you can see that here we're going from minus 20 to 0 over a 1-decade interval. We flatten out in this range between 0.1 and 10, and then we start rolling off at 20 dB per decade for frequencies higher than 10 radians per second. The phase begins to activate a decade before the first pole, which the first pole was at 0.1. So at 10 to the minus 2, we start to see some transition in our phase, and that now we do it with an approximation of a straight line, and it quits. Our poles stop contributing phase slope beyond 100 in our straight line approximation, and that's what we're seeing here in this phase plot via the MATLAB commands. And that is then a validation of what we have just sketched in our Bode plot by hand.